All right, guys, so this is going to be part 3 here. We'll just do a quick, try to break the videos up into little chunks so you guys can take breaks or whatever, right? So we're going to take, all I need to do for this question, okay, I just want to draw something that satisfies these conditions, nothing too crazy, okay? We're just going to draw something, okay? So there are two different conditions here as denoted by the comma, one of which is the fact that one of these is a point. When I plug in -3 into whatever function I draw, I see that the point is, or the y value is going to be 0. So there is a physical point that I need to draw that takes care of this condition though. Okay, and then I can pretty much draw it. The other part here is just telling us that there is a like a limit as x approaches -3. We're going to have a y value of 3, right? So why don't we just draw, I don't know, just for not consistency's sake, but just something, I don't know, that satisfies this condition, right? And then you could draw pretty much anything you want, right? Those are the two conditions. We don't know what the function actually is, but we could just draw that, okay? Okay, so the second one here, as it looks like, as I approach 2 from both sides, I get different numbers. Okay, so we're going to see, we should expect to see a jump here, right? I don't know what you would like to draw, but I don't know, I'll draw something. So at x equals 2, we see two different y values, right? We're going to see, there's a point at 1 and -1. Okay, so we could just draw. Let's go put on these 2 points. Well, when x approaches 2 from the left, so something like this, my y value is going to be, I don't know, -1. And then when x approaches 2 from the right, we get 1. Right? And we see that there is a jump, right? At x equals 2. Okay? So I suppose over here we could call something like this, we could call this a what we call a removable discontinuity at x equals 3. Okay, so if we jump down to number 4 here, and this is going to be it, okay, for this morning's portion of the lessons, okay, so the function p of t describes the production of unleaded gasoline in a refinery in thousands of liters where the time t is measured in days. Okay, so we want to evaluate the limit as t approaches 1 of the actual function, right? So we just want to see what the value is graphically. It looks like just as the time value approaches 1. Okay, so we're just going to have a look. Okay, so, well, let's evaluate the limit, right? We're just actually, I don't even need to rewrite this. We're just going to evaluate what the limit actually is, right? Well, it looks like when t is approaching 1, right? So as I get closer and closer and closer and closer and closer to 1, it looks like the value is going towards 30. Okay. And then if I was to take a look at the limit, should I jump down to part B here? The limit as t approaches 3 from the left and the right, right? So we're going to have a left-hand limit and a right-hand limit. So let's do the left-hand limit, or left side limit. That's going to be when as t approaches, we better follow convention here, the limit as t approaches -3, not -3, 3 from the left of the function pt. Well, that's going to equal, what's the limit? As the graph approaches 3 from the left, remember this is the value of 3, as it approaches that value from the left, we're approaching but never actually touch 3. Okay, and then we have a right side limit where we evaluate the limit as t approaches 3 from the right, right? What's the limit as t approaches 3 from the right? Well, here's our right side of the graph. So I'm approaching 3. Oh, we actually get to, oh, I gotta write the function. That's equal to 3. 3, 0, 0. Okay, so there's obviously a discontinuity here, right? Or there's a jump in the graph, right? Okay. And then these are just some questions that we can look at, right? Well, it looks like the refinery, right? The refinery was shut down for lunch or whatever, right? Down on day 3. Sorry, I forgot that the T was measured in days. On day 3. And then opened again. I was thinking that this was in like time for hours, and this was like a lunch break or something too. That would also work, right? There'd be a lunch break for, I don't know, 2 hours or something, and then they kick back up again, right? But it's in days, so opened again on the 5th day. Okay, and then we know that the graph, as a result, p of t, the function p of t, is discontinuous at t equals 3 and t equals 5. And then we can say, well, what time was production highest and what time, and what was the rate of change of production at this time? Okay, well, production, it looks like, if we were to look at the actual graph, it looks like the production is highest here, right? And remember, P of T is a production, right? So production was highest. T equals 2 on day 2. Okay, but the catch here is, though, if we were to actually, like, let's say we were to actually do, we were like provided with a P of T function, right? We were provided with a P of T function and we applied our first principles, we would see that the slope of this line would come out to be 0. And that's consistent with some of the things that you guys would have seen, like with quadratics, for instance, right? That's reminding me of a quadratic graph where we found the maximum of something, the slope at that maximum, like let's say what was the maximum height of a ball reached or something like that, its slope at that maximum height was 0, right? So the rate of change at t equals 0, t equals 2, sorry, was 0. Because this is like a turning point, right? That's what a maximum or minimum is. It's a turning point between the negative tangents turn into positive tangents, but there has to be one single tangent in the middle of those two scenarios where the slopes are all negative and then they turn around and go positive. There has to be a moment in time where the slope goes to 0, or the slope of the tangent, right? And so that's what we're seeing there. There has to be a moment in time where there is, production's very, very high, starts slowing off, and then, sorry, I'll draw that on here. The production slope of the tangents are all very high. It starts slowing down. And eventually, in order to actually turn around and start seeing negative, like slower production rates, there has to be a moment in time where there is a slope value of 0, or m of the tangent. Okay, so that's it for this morning stuff, and I'll get this afternoon stuff posted shortly.